This video has a seizure warning. If you're prone to seizures, look away. So I've got a cat. His name is Charlie, and he's a handsome little guy. He's got some white fur, he's got a couple of brown spots, and overall, he's a pretty cute cat. So what I decided to do was I wanted to see what Charlie would look like as a robot, and so I wrote a script to do that, and here's what it looks like. Charlie does look like a pretty cute robot here, but then I started wondering what would he look like as a marble sculpture. This one looks slightly more horrifying, but then I started wondering what would he look like a fiery god. And this looks completely terrifying. So today I'm going to show you guys how to run Stable Diffusion on your local computer so that you can also make videos like this. And it's super easy. You don't even need a super powerful computer for this, and we can probably get it done pretty quickly. So let's get started. So Stable Diffusion is a machine learning model that allows you to generate an image when you give it a prompt. So you can ask for an astronaut riding a horse, you could ask for whatever this is, and really anything you can put in a prompt, it might generate something interesting. So Stable Diffusion's been around for a while, and what I'm going to be showing you guys today is how to use the instruct pix to pix model so that you can supply an image, give it a prompt, and your image will be transformed according to the prompt you give it. And this isn't amazing, like it doesn't work perfectly, especially on videos, but you don't really need a super powerful computer to run this, so it's a good little practice for getting into machine learning. Before we get started, I'd highly recommend you have a good GPU for this. Any GPU with CUDA enabled should do the job. I've got a RTX 3070, so it's not amazing, but it gets the job done. I'm using Linux, but you can make it work on Windows or Mac with some tinkering, but it's just a lot easier on Linux. Like I just mentioned, I'm going to be adapting the instruct pix to pix model so that I could pass in a video and generate a stably diffused video. So what it's going to do is it's going to go through every single frame in the video that I pass in, run Stable Diffusion on it, and then output a video that you could play back. And I'm going to be using Python 3.11 for this. So to start off, just create a folder and put in your source video. I'd recommend having a short video, especially if you don't have a great GPU, because you will run into issues where you run out of memory if you have a huge high quality video. I've got this requirements text file here, but you don't need it. You can check out my GitHub, the link will be in the description so that you can see all of the different versions that I used. So we're going to need three things from the command line. We're going to need the source video, we're going to need the frame rate of the source video, and then we're going to need some sort of prompt so that we could transform the video. So now that we got that, the first thing we need to do is take our source video and cut it up so that it's a bunch of images. And we need to do that because the instruct pix to pix pipeline requires it to be an image and not a video. So we just need to use a thing called ffmpeg so that we can transform the video into a couple hundred images. We're going to need a place to store these images, so I'm going to create two directories, input and output. Input will be where all of the frames of the source video will be stored, and output will be where all of the diffused images will be stored so that we could then turn that into a video. We're using ffmpeg, which allows us to use our source as the input, and we're going to slice up the video so that we can capture every single frame in the video. The frames will then be stored under input so that we could then use it later on in the script. The next thing we want to do is initialize our diffusion pipeline. So we're going to be importing Stable Diffusion instruct pix to pix and the Euler ancestral discrete scheduler from diffusers. So this line is basically saying we want to use the Tim Brooks instruct pix to pix pipeline so that when we pass in the image, it's going to go through that pipeline and do whatever that pipeline needs to do. We're going to make sure that the pipeline is running on CUDA because I want to use my GPU to compute all of this. The CPU will be far too slow, so we just want to specify that we're using CUDA, and then it will use my 3070 graphics card. We're also using the Euler ancestral discrete scheduler, so we just want to set that into our pipe. And then we can now move on to actually transforming the images. For each image in our inputs directory, so these are all the frames of our source video, we want to diffuse the images. We want to run it through the pipeline so that we can change the image and make it look weird. The next thing we need to do is create this diffuse function. We need to use a package called Pillow so that we can transform the image into something that the pipeline could understand. We're going to open the image in Pillow and we're going to convert it to RGB and set the EXIF transpose so that we can have a well-formatted image that we can then pass on to the pipeline. Now that we have that done, we can actually put the image through the pipeline. So we're going to call the pipe function and we're going to pass it in our prompt. So this could be something like turn the cat into a robot or turn the cat into a marble statue. We're giving it the image and we're going to give it the number of inference steps. The higher the number is, the better your image will come out, but it will take a lot longer to compute and generate the image. After that, we're going to save the image to our output file so that we can then access it later to turn all of the images in the output into a video. To turn the images back into a video, we're going to use ffmpeg again. This time, our input is going to be the frames in our output folder. This line is basically telling ffmpeg that the frames are in number order, and that is the order that we should combine it into. We're using the sequence pattern, and that's because I didn't pad the frame numbers with zeros, so we can't use glob. Sequence just makes sure that 9 comes before 10. Otherwise, it would look at 1, 0 rather than 10 as a whole. We're using the frame rate that we'd specified earlier, and we're going to output it to an MP4 file called output, and that'll show up in the same directory that our script is in. And we need to use the format YUV420p so that the MP4 could actually be playable. This handles the encoding inside of the MP4 and the metadata, and without it, the video will not work. And lastly, we just want to delete those input and output folders so that we can have a clean directory. This was a super simple script. It was only 50 lines, and now we can actually run it. So let's give it a shot. I have the source video in my directory. I have the script, and now I can run it. I'm going to do python main.py, pass it in my source video, so that's called catmov. And the video that I took was 60 frames a second, so I'm just going to pass it in 60. Yours might be different. It could be 30, it could be 24, but I shot it on my iPhone and it was 60 frames. And now we need to set the prompt. I'm going to do turn the cat into a robot. So let's let it run and let's see what happens. It's going to take a while, and you'll be able to see the progress of it by looking at whatever's in the output folder. So if I go into output right after this first one loads, we'll see we have a robot cat. It takes me about 20 or 30 minutes to generate it all, but in the end, this is the result. It isn't amazing for videos, but it is pretty cool, and I'm sure you could do something creative with it if you have a simple video. The more things there are on the screen to process, the harder it'll be to distinguish, so that's why you see some artifacting over here. It can't detect what is a cat and what isn't, especially given that I only did 15 steps for the model. But if you have a stronger computer, you can increase the inference steps and you might get a better image. So that's it. Thanks for watching. And check out the code on my GitHub. It's got some pretty decent documentation. It's got it all written out. So hopefully it should be pretty easy for you to run this on your own computer. And see you next time.